In the periodic table, there exists a row of elements often relegated to a footnote. They are detached, floating at the bottom like an island of misfits. To the casual observer, they are the lanthanides, a difficult-to-pronounce cluster of metals with tongue-twisting names like praseodymium, dysprosium, and ytterbium. But to the geologist, the physicist, and the geopolitical strategist, these 15 elements, along with their cousins scandium and yttrium, are known as the rare earth elements. They are the invisible skeleton of the 21st century. Without them, the digital age would quite literally cease to exist. There would be no smartphones to connect us, no electric vehicles to drive us toward a greener future, no fiber optic cables to carry the internet across oceans, and no precision-guided missiles to define modern warfare. They are the vitamins of modern industry. They are required in small doses, but they are absolutely vital for health. Yet despite their name, they are not rare. Cerium is more abundant in the Earth's crust than copper or lead. Thulium, the rarest of the stable lanthanides, is more common than iodine or gold. Their rarity is a geologic and chemical paradox. While they are everywhere, they are almost never found in concentrated, economically viable deposits. They are chemically promiscuous, bonding readily with other elements and scattering themselves diffusely across the planet's surface. Worse still, they are social creatures. They are almost always found mixed together, and separating them is one of the most difficult challenges in chemical engineering. Today, we are going to explore the total landscape of rare earth elements, from the quantum mechanics of their electron shells to the acid-drenched processing plants, and finally to the boardrooms where nations vie for control over these elements of power. To understand why a wind turbine needs neodymium, or why a missile guidance system needs samarium, we must zoom in to the atomic level. The magic of rare earths lies in their electron configuration, specifically in the filling of the 4f orbital. In most elements, the valence electrons, which are the ones that do the chemical bonding and determine properties, are on the outside of the atom. When you look at carbon or iron, their chemically active electrons are exposed to the world. Rare earths are different. As we move across the lanthanide series from lanthanum to lutetium, electrons are added to the 4f subshell. However, this 4f shell is spatially buried inside the atom. It is shielded by the filled 5s and 5p shells, and even the outer 6's electrons. This means the 4f electrons are largely protected from the surrounding environment. They do not participate strongly in chemical bonding, which is why all rare earths behave so similarly chemically. They all generally form +3 ions and look identical to a standard chemical reagent. But physically, these 4f electrons are the source of the magic. Because they are unpaired and shielded, they retain their atomic magnetic moments, even when the atom is locked in a solid crystal. In iron or cobalt, the crystal structure can quench magnetism. In neodymium or dysprosium, the 4f electrons act like tiny, isolated bar magnets that refuse to be bullied by their neighbors. This allows for the creation of super-strong permanent magnets. The defining feature of rare earth chemistry, and the bane of every process engineer, is the lanthanide contraction. As you move from left to right across the periodic table, you add protons to the nucleus and electrons to the shell. Usually, the extra electrons shield the outer shell from the extra positive charge of the nucleus, so atoms get slightly bigger or stay the same size. But 4f electrons are terrible at shielding. They have a diffuse shape that does not effectively block the pull of the nucleus. Therefore, as we step from lanthanum to cerium to praseodymium, the increasing positive charge of the nucleus pulls the outer electron shells tighter and tighter. The result is a steady, predictable shrinkage of the ionic radius across the series. Lanthanum is about 1.03 angstroms, while lutetium shrinks down to 0.86 angstroms. This might seem trivial, but it is the only real difference chemists have to work with. Because their chemical reactivity is nearly identical, we cannot separate them using standard chemical reactions. We must exploit these tiny differences in size to separate them, a process that requires thousands of repetitive steps. Now, if rare earths are everywhere, why are mines so rare? The answer lies in mineralogy. While rare earths substitute easily into common rock-forming minerals, they rarely form their own concentrated minerals. When they do, they fall into two primary categories: hard rock deposits and ionic adsorption clays. The most famous rare earth mines in the world, such as Bayan Obo in China and Mountain Pass in California, are hosted in carbonatites. These are bizarre, igneous rocks. While most volcanoes spew silicate lava or molten glass, carbonatite volcanoes spew molten calcium carbonate, which is essentially washing soda and limestone. In these strange geologic melts, rare earths are concentrated into specific minerals. First, there is bastnasite, a fluorocarbonate mineral. It is the primary source of light rare earths, like lanthanum, cerium, and neodymium. It is relatively easy to process, but often contains radioactive thorium. Then there is monazite, a phosphate mineral. It is richer in heavy rare earths, but is inextricably linked with thorium, making it radioactive and politically difficult to mine in many Western jurisdictions. In the subtropical hills of southern China and Myanmar, a different type of deposit exists, known as ionic adsorption clays. Over millions of years, granite rocks rich in rare earths have weathered in the warm, acidic rain. The rock breaks down into clay, and the rare earth ions are released. Instead of washing away, these positive ions get stuck, or adsorbed, onto the surface of the negatively charged clay particles, much like a magnet sticking to a fridge. These deposits are low-grade, often containing less than 1% rare earths, but they are incredibly valuable. You do not need to blast rock or crush ore. You just need to wash the clay with salt water, specifically ammonium sulfate, and the rare earths pop off. Furthermore, these clays are the world's primary source of the lucrative heavy rare earths, like dysprosium and terbium, which are needed for high-temperature magnets. But mining is just the easy part. The true bottleneck in the global supply chain is processing. Turning a chunk of ore into a pure metal oxide is a feat of chemical endurance. For hard rock mines like Mountain Pass, the ore is crushed to a fine powder. Using a process called froth flotation, specific chemicals are added to a water tank. These chemicals attach only to the rare earth minerals, making them hydrophobic or water-fearing. When air bubbles are blown through the tank, the rare earth minerals cling to the bubbles and float to the surface, forming a froth that is skimmed off. This concentrates the ore from about 8% to 60%. The concentrated ore is then baked in a kiln with concentrated sulfuric acid at temperatures up to 300 degrees Celsius. This terrifying process cracks the mineral structure, converting the insoluble phosphates and carbonates into water-soluble sulfates. The result is a liquid soup containing all 17 rare earths plus iron, uranium, thorium, and other impurities. This leads us to the heart of the industry, solvent extraction. We now have a liquid mix of rare earths. How do we separate neodymium from praseodymium when they are chemically almost identical? We use a technique relying on two immiscible liquids, an acidic water phase containing the rare earths, and an organic phase like kerosene containing a special extractant molecule. These extractant molecules are designed to grab rare earth ions. However, because of the lanthanide contraction we discussed earlier, they grab heavier, smaller rare earths slightly more tightly than lighter, larger ones. The separation factor between adjacent elements is tiny, often less than 1.5. To get 99.9% purity, you cannot do this once. You must do it hundreds or thousands of times. A typical separation plant looks like a sea of blue plastic boxes called mixer settlers. The liquids are mixed so the transfer happens, then allowed to settle so they separate. A single separation line might have 1,000 mixer settler units connected in series. This process is chemical brute force. It consumes vast amounts of acid, alkali, and water. It is finicky. A slight temperature change or impurity can ruin the separation, forcing the plant to recycle the liquid and start over. Why do we go through this trouble? Because modern technology is impossible without them. The single most important driver of the rare earth economy is the permanent magnet. The neodymium iron boron magnet is the strongest permanent magnet known to physics. The crystalline structure locks the magnetic moments of the iron atoms into alignment. The neodymium atom provides magnetocrystalline anisotropy, basically acting as an anchor. The 4f electron shell resists turning, preventing the magnet from demagnetizing even under strong opposing forces. However, pure neodymium magnets lose their magnetism at high temperatures, above 80 degrees Celsius. This is useless for an electric vehicle motor, which runs hot. The solution is adding heavy rare earths, like dysprosium or terbium. By replacing some neodymium atoms with these heavier elements, the magnet's resistance to heat skyrockets. A single offshore wind turbine can contain 2 tons of these rare earth magnets. Beyond magnets, if you are reading this on a screen, you are looking at rare earths. Europium is the only element that produces a perfect narrowband red light. Without europium, there were no color CRTs, and there would be no rich red LEDs today. Terbium provides the brilliant green phosphor. Yttrium acts as the host matrix for white LEDs. Then there are catalysts and polishing. Cerium is the workhorse here. It shuttles easily between oxidation states, making it perfect for catalytic converters in cars. It is also used for chemical-mechanical polishing. Silicon wafers for microchips must be atomically flat. Ceria slurry is used to polish them. It does not just scratch the surface. The cerium chemically reacts with the silicon, softening it while mechanically wiping it away, a dance essential for semiconductor fabrication. This brings us to the geopolitics of dirt. For most of the 20th century, the US dominated rare earths via the Mountain Pass mine. But in the 1980s and 90s, a shift occurred. China possesses the geological lottery ticket, the Bayan Obo deposit in Inner Mongolia, the largest deposit on Earth. Deng Xiaoping famously said, "The Middle East has oil. China has rare earths." China recognized the strategic value early. They subsidized production, keeping prices artificially low and driving Western competitors into bankruptcy. They integrated downstream, meaning they did not just want to sell the oxide dust, They wanted to sell the metal, the alloy, the magnet, and the electric motor. They also invested heavily in research and development, creating a massive knowledge gap that the West is now struggling to close. By 2010, China controlled 97% of global production. That year, following a maritime dispute with Japan, China unofficially blocked rare earth exports to Japan. Prices skyrocketed. Neodymium went from $15 per kilogram to $500. The world woke up to its vulnerability. As of the mid-2020s, the supply chain has diversified, but China still retains a chokehold, particularly on processing. While mining happens in the USA and Australia, China controls about 90% of refining capacity. In late 2025, the situation escalated when China updated its export control list to include manufacturing technology, posing a direct threat to Western efforts to build independent supply chains. A dark secret of the industry is Myanmar. It has become the world's third largest producer, specifically of the heavy rare earths crucial for magnets. The mining is concentrated in areas controlled largely by militias. The mines are often illegal operations using in-situ leaching without environmental controls, pumping ammonium sulfate directly into hillsides. The resulting solution is trucked across the border into China for refining. This laundered material ends up in global supply chains, posing a major ethical dilemma for global tech companies. This leads us to the environmental cost. The separation of rare earths is chemically dirty. Radioactivity is a constant issue because monazite and bastnasite almost always contain thorium and uranium. Crushing the rock liberates radioactive dust, and waste must be managed carefully. In Baotou, China, the tailings pond is a massive, toxic lake filled with the black sludge of decades of processing. It is a visceral reminder of the entropy required to create our ordered, high-tech devices. So what is the future frontier? The world is scrambling to solve the rare earth problem. Western companies, like MP Materials in the USA and Lynas Rare Earths in Australia, are building independent supply chains. However, they face the balance problem. Mines produce elements in fixed ratios, lots of cheap cerium, but less of the valuable neodymium. Western mines struggle to be profitable because they have to sell the excess cerium at a loss, whereas Chinese producers can absorb these imbalances. Recycling, or the urban mine, is another frontier. Billions of phones contain thousands of tons of neodymium. But recycling is hard. You have to disassemble the device and chemically separate the rare earths. New technologies, like flash Joule heating, are being developed to make this viable. Then there is deep-sea mining. The Pacific Ocean floor is covered in nodules rich in rare earths. While technically feasible, it faces immense opposition from environmentalists. Finally, there is substitution. Tesla has announced next-generation motors using permanent magnets with zero rare earths, likely using advanced iron alloys. Rare earth elements are the perfect symbol of our complex civilization. They are chemically fascinating, leveraging quantum mechanics to bend nature to our will. They are geologically abundant yet economically elusive. And they are politically charged, sitting at the fulcrum of trade wars. As we move deeper into the green energy transition, our hunger for these elements will only grow. Securing a sustainable supply of these industrial vitamins is one of the defining challenges of our time. We have pulled the magic dirt from the ground, now we must learn to wield it wisely.